Okay. So let's see. Let's discuss a little bit about bypass transition. So bypass transition, one of the very this is actually currently one of the pretty active research fields out there to have a better model of what actually triggers bypass transition. So if you look at what's currently being used, all the bypass transition models are very crude models, like this one appeared in our textbook. So the observation, this model is coming from a very general but very noisy observation that the location of the transition, particularly RE theta, the thickness of the boundary layer, is sensitive to the boundary layer profile, to the pressure gradient, if the turbulence level is relatively low. Okay, so for example, this 1 minus the turbulence level divided by this empirical parameter is close to 1, then the transition location is modeled as an exponential function of this quadratic function of f, a quadratic function of lambda. The lambda is the Thrice parameter, basically modeling the pressure gradient locally. But when the turbulence level is high, so when this number is close to 0, then the location of the transition is pretty much dominated by how turbulent the free stream is, and it's less sensitive to whatever pressure gradient you have on the flow. So basically, whatever you have here is going to be multiplied by something close to 0, and this 163 is basically, it's very close to where you transition when the turbulence level is very high in the free stream. Okay, so it's just a very crude empirical model, and there is a lot of current research going on in trying to make better models out of this, and using direct numerical simulation data or machine learning and things like that. Okay, last we want to talk a little bit about receptivity. So usually if you look at the same frequency, okay, so for typical thickness of the boundary layers, if you look at the sound wave and TS wave of the same frequency, they look very different. The sound waves, if you plot it in spatial scales, are much longer in wavelength than the unsteady TS waves. So there was a long-standing, so after people did the theoretical analysis of the growth of the TS waves, and people actually saw the TS waves in experiments, there was still a very big question, is how does the TS wave begin to develop? It is not something you can measure in experiments, just because the TS waves are so low in amplitude in the beginning. So the question of how does it first get into the boundary layer is a big question that nobody knows how to answer. But later on, people discovered various mechanisms for long wavelength signals to travel into the boundary layer and become small wavelength signals. So one of these ways is a small roughness element, or basically a small geometric feature embedded in the boundary layer. Okay, the geometric feature can be of the same order of spatial scale as the unsteady TS wave, or it can be much smaller, because if you have a small geometric feature, it can create longer wavelengths. But it's hard for longer wavelengths to create shorter wavelengths. So if you have a feature like this, when the long acoustics waves hit this geometric feature, if you look at the Navier-Stokes equation, there is a mechanism for the pressure waves to translate into entropy waves. And then you're going to have a conversion mechanism that converts that converts spatial length scales of L into length scales of L over U, L times U over C, where C is the speed of sound. Okay, so if you have a geometric feature like this, you can convert wavelengths of L into wavelengths of L times U over C. So U is usually a lot smaller, so you get a smaller wave to start your TS wave growth. Another mechanism is that if the boundary layer doesn't have this roughness, but creates an external pressure variation that causes my H, the shape factor of the boundary layer, to vary within a certain spatial length scale, then it can also be a way for the sound waves to translate into TS waves, because different shapes of boundary layer, they respond to pressure gradient from the sound waves differently, right? So if you have a bigger H, it responds more to any pressure gradient, right? And if compared to if you have a lower H, so higher H has a larger portion where you have slow velocity, and slow velocity responds to pressure gradients a lot more, because like you have U partial X equal to minus partial P partial X, right? So if U is slow, the ratio between right, so the ratio between the response to the forcing is a lot higher, right? So you get more change in the velocity out of the same pressure gradient as a lower H region, and that creates spatial non-uniformity in the boundary layer itself that oscillates at the same frequency as the sound wave, but at a much smaller spatial frequency. So that's another way for the boundary layer to accept disturbance from the free stream. And one of the consequences of this is that if you want a flow that is very resistant to natural transition, you want to avoid this kind of non-smoothness or rapid change in the boundary layer profile. And that's another reason I just discussed another lecture, is that if you have a leading edge of a compressor blade, you don't want this leading edge to be really sharp, because a really sharp leading edge is a very good receptivity site. So that is, you can either see this leading edge as something like this, or as something like this that creates a rapid variation in the shape factor. Either way, it's going to effectively translate disturbances from the sound waves or from larger scale turbulent structures into small scale TS waves that can lead to transition. So basically, receptivity is going to increase or decrease your critical N factor, right? If you don't have these receptivity sites, it can increase your N. If you do have these, it'll decrease your N.